Hello, in this video we are discussing implicit representations for 3D shapes. To this end we will cover comparison of implicit versus other 3D representations of shapes and a number of reconstruction techniques that aim to estimate implicit functions from sampled data. We'll start with a recap of implicit functions. So the implicit function machinery assumes that there exists a function which maps points in the three-dimensional Euclidean space to a real line, with values greater than 0 outside the shape and lower than 0 inside the shape. Such a function is often called the sign distance function of the particular shape. The zero-level set of this function is the set of 3D locations which correspond to the surface of the object. This machinery is tightly connected to the occupancy map and sign distance function and truncated sign distance function that we have been discussing in the previous video, meaning that the implicit function can be defined over a voxel grid, which makes it essentially basically a regular representation. So the simplest volumetric representation of the implicit function, or the SDF, is the dense discrete volumetric grid. This makes it also similar to raster images in photography or to range images in our course. So in each cell, we basically store a signed or unsigned and possibly truncated distance value. In the previous lecture, we have discussed how the memory footprint of this computational representation scales cubically as the resolution along each spatial dimensions increases. However, we can also define SDF or TSDF values at XYZ coordinates of the 3D points. And this is something that we will do later in this video. So an implicit function does not have to be defined on a regular volumetric grid. Instead, we can define it in arbitrary locations in 3D space. For example, in the point cloud that samples the shape. Because the point clouds are noisy and contain outliers or misalignments, this means that eventually some of the 3D locations represented by the point clouds are going to store non-zero values of the sign distance function. Surface reconstruction is the method of creating a surface representation from sparse input points. This week, we're going to learn how we can create implicit surface representations from the input points. This means that we will be feeding an implicit function to recover a sign distance function with basically values less than 0 inside the shape and greater than 0 outside of the shape. Some of the reconstruction algorithms that we will cover today include radial basis functions, moving least squares, and Poisson surface reconstruction. However, we will also cover neural network-based approximators to the implicit surface representation. Let's start with a reconstruction problem setting. You can recall that stitching or reconstruction is one of the steps within the geometry acquisition pipeline where all of the range images or depth maps have been brought together to a single coordinate frame and now represent a denser point cloud. Then reconstruction can be performed, which goes from an unorganized set of points eventually to the surface mesh, typically by integrating all of the points into a continuous implicit function of the shape. For instance, within the digital Michelangelo project, the authors were able to actually integrate 1 billion sample points into an 8 million triangle mesh for a number of objects that represent significant interest within the context of the cultural heritage preservation. As you can see, the resulting meshes are very clean and very detailed at the same time. Obtaining such high-quality 3D reconstructions is challenging in the framework of geometry processing. Typical inputs to the reconstruction process can basically vary depending on how the 3D measurements are viewed. For instance, if the point cloud comes as a completely unstructured point set, then it might be convenient to just consider them as a set of 3D points that are irregularly spaced in 3D space. Commonly, to obtain a more robust 3D reconstruction, we will have to orient the surface, and to this end we will have to estimate the orientation of each individual points. Specifically, we'll have to estimate per point normals. This is a lot to ask, but most of the reconstruction algorithms are able to benefit and leverage this information. However, another input option might be that the normals come from the range scans, because these depict particular views of the object by the camera or a depth sensor. Because the camera views the object from a particular direction and is located outside the object, we are able to actually obtain estimates of point orientations automatically. The simplest way to obtain a mesh from points would be to basically connect nearby points by edges, ensuring a coherent structure of the mesh. This is an old technique presented in the 1994 article by Greg Turk and Mark Lavoie. However, stitching the range scans together may bring holes or non-manifold situations. So this ensures that we exactly interpolate single points, but can be bad for a noisy or misaligned data, and also potentially lead to self-intersections in the mesh, which generally means a poor or unusable mesh in the end. The goal of an implicit reconstruction, however, is significantly different. We start with a set of range scans. These can typically be equipped with inherent connectivity informations. That is, they can be viewed as a set of range surfaces rather than range scans. We will further remove the existing connectivity, if any, between the adjacent vertices. So we just view them as a set of 3D points. Our goal will be to basically approximate input points by fitting a function through that pass nearby the points. If we succeed, this will lead to a watertight manifold results. So this is exactly where the implicit representation of the shape comes into play. Implicit representation of the shape connects the dots by a continuous curve, typically smooth or otherwise continuous, and has the values greater than 0 outside the shape and lower than 0 inside the shape. If we compare reconstructions obtained using implicit and explicit methods, we can see that the implicit method typically is able to generate a more uniform reconstruction, including the surfaces where we have little or no data points. On the contrary, explicit reconstruction methods can potentially produce non-manifold or non-uniform meshes. One of the key ingredients in defining the signed distance function is to associate an oriented plane with each of the data points. These tangent planes basically serve as local linear approximations to the surface. It's relatively easy and simple to construct the tangent planes. However, the selection of their consistent orientations is a challenge. So normals, if they are available, will help to distinguish between inside and outside. Moreover, tangent planes do not directly define the surface, and their union may have a complicated and non-manifold structure. In any case, we will use tangent planes to define the SDF, a signed distance function to the surface. Consider a point in the vicinity of the surface. Our goal is to estimate the f of x, which is the distance to the surface. This function is potentially discontinuous at certain points. The discontinuities result from the implicit partitioning of space into regions within which a single tangent plane is used to define the signed distance function. The original paper by Hoppe computes the tangent plane slightly differently by using PCA on KNN graph of each of the data points that they call the Riemannian graph, but the consequences are still the same. We wish to instead find a function which implicitly defines a surface and also satisfies equations f of pi equals 0. Here pi are points lying on the surface. Our core assumption will be that they interpret the function as smooth. One issue, however, is that the trivial solution is very easy to obtain, and the trivial solution is that f is 0 everywhere. To avoid that solution, we append off-surface points to the input data and give them non-zero values. This gives a more useful interpolation problem where f of pi plus epsilon n sub I equals epsilon or minus epsilon. Off-surface points may be assigned either side of the surface, as illustrated in the figure. However, experience has shown that it is better to augment a data point with two off-surface points on either sides of the surface. There still remains the problem of generating the off-surface points and the corresponding distance values. So given a set of zero-valued surface points and non-zero off-surface points, we now have a scattered data interpolation problem. We want to approximate the signed distance function by an interpolant f. This function is a particular example of a radial basis function. So basic functions phi is a real-valued function that is defined in a domain from 0 to infinity. It's commonly unbounded and of non-compact support. In this context, the points c sub I are referred to as the centers of the RBF. Popular choices for the basic function phi include splines and the Gaussian function, for example. The goal with radial basis function interpolation is to find the weights w by interpolating the constraints where the triple of c 3i, 3i plus 1 and 3i plus 2 is equal to the on-surface and off-surface points observed in the point cloud. To do that, we construct a linear symmetric system to actually get the weights w from the radial basis function equation. Inverting the matrix in the left side of the equation yields us the weights, and plugging the weights into the formulation of the radial basis function, we get the actual prediction in each point inside or outside the surface. The question is, of course, how do we choose the kernels or the basis functions? So, for example, one popular choice of the kernel is the tri-harmonic kernel. That is, it's symmetric, and it's represented by the cubic function defined on the distance between the 2 points. It is globally supported, lives in dense symmetric linear system, and also ensures smoothness up to the second derivative, and works well for highly irregular sampling. However, other choices include polyharmonic splines or multi-quadric, Gaussian, and B-splines with compact supports. Some of the results obtained using the RBF reconstructions are presented in this slide. Interestingly, the number of points in a point cloud typically exceeds the number of RBF kernels that is required to represent this point cloud by an order of magnitude. One important issue when defining the RBF-based reconstruction is how do we actually add off-surface points to the linear system that we're solving. We typically are given a set of surface normals, but then we must be careful when projecting off-surface points along the normals to ensure that they do not intersect other parts of the surface. The projected point is constructed so that the closest surface points is the surface point that generated it, actually. In this slide, you can see the effect of insufficient number or badly spaced off-surface points as compared to properly chosen off-surface points. If we compare visually reconstructions obtained using a number of various sign-distance function reconstruction algorithms, such as distance to plane, which is piecewise linear compact RBF, and the global tri-harmonic RBF, we can see that the latter basically yields you the more smooth solution, for example, for this case of a sphere sampled with a point cloud. To summarize the RBF part, the radial basis functions basically provide you a global definition of the SDF, and this is an advantage because they actually provide you a global model for the entire shape, and also they offer a way of globally optimizing the weights, even if the basis functions are inherently local, such as the Gaussian kernel, for example. It is also conceptually simple, as it only requires you to solve for the linear system. Moving least squares is another example of purely local reconstruction method that also leverages the same premises as the RBF. So with moving least squares, what we do is we select a neighborhood in the augmented point cloud, and by augmented we mean that we take the point cloud and also the associated normals, and we create additional off-surface points. In the slide they are marked by the plus epsilon or minus epsilon points. And so we create 3 points for each of the original sensed point cloud points. And by moving the neighborhood across the sample, we fit a local polynomial to each of the neighborhoods captured by this local sphere, and the idea is that we obtain a globally smooth solution, but only do local approximation. So let us consider this in greater detail. So moving least squares approximation with polynomials amounts to choosing a degree k of the polynomial and considering the set of polynomials up to degree k in each of the variables x, y, z. So there exists a particular number of polynomials of such degree, of up to such degree, and we form basically the most general polynomial b of x, where x is the xyz coordinates of each point, and the polynomial can be expressed by multiplying the basis functions of the polynomial b of x by a set of coefficients a. And our goal would be to find the coefficients, of course, that minimize the sum of squared differences from the xyz points in the surface to the distance values. However, for the moving least squares formulation, we allow the fit to change depending on where we evaluate the function. This can be seen as the coefficients varying with x as well. And we do so by weighting each row of the equation below by a theta of x minus c sub I, where theta is some distance weighting function, which gives us a weighted least squares approximation. An interesting idea is that we really now want to find the a sub x that minimizes this weighted sum of squared differences, and the value of the SDF is the obtained approximation evaluated at each point in space. So the difference between the vanilla global approximation using, for example, quadratic function is that for a global approximation you only solve for 3 coefficients and you obtain a global solution that is defined everywhere using just a single polynomial and a single set of weights by minimizing the least squares objective. However, with the moving least squares approximations using the same set of functions, what you get is a much more complex function because you allow for your coefficients to vary spatially. Of course, again, a question arises: how do we select an appropriate weight function? So in fact, many functions have been tested, and to select an appropriate weight function, it's basically you can select depending on whether you would like to obtain an interpolating or an approximating behavior, and it is possible to achieve even with low order basis functions. So for example, a weight function that, for example, approaches plus infinity at 0 with basic will generally cause interpolation. So for example, the singular function will cause you an interpolation, and that is depicted in the lower part of the slide here. So depending on the weight function, you will be obtaining either interpolating or approximating behavior. So for example, the MLS with nearly singular weight functions, like described above, is going to be exactly interpolating the points, because it will only select, basically will only leave on the points exactly, and will try to only basically interpolate you the interpolatory behavior. However, if you choose a different weight function, such as the Gaussian, for example, you will get approximation behavior with the function no longer passing through any of the data points, but with a function that is going to be much more smooth. Depending on the weight function, the MLS is function is continuously differentiable if and only if the weight function is continuously differentiable. And basically, anyway, the MLS approximator f is as smooth as the theta function that it uses. Some examples of reconstruction using the MLS function is depicted in this slide using a Martian cubes extracted surface. As you can see, we create for each of the blue points that represent the original point sample, we create 2 additional off-surface points and theta global SDF using MLS. As you can see, in this case, this is an approximatory MLS, and we basically get a very smooth reconstruction in this case. One possible improvement with MLS leverages this observation. So if we define a surface by only requiring it to take a given value on the surface, we will not obtain useful results. What we can do is add the pseudo-normal constraints by placing a 0 constraint at the point on the surface, a positive constraint offset slightly outside, and a negative one slightly inside. So this is just the same way as we have been observing before with the off surface points. And unfortunately, this approach does not work as well as one might like. The additional constraints influence the function's gradient very crudely, and this can cause undesirable oscillatory behavior as the evaluation point moves away from the surface. So this behavior is illustrated in a figure on the slide. It occurs because when the distance between the evaluation point and the surface point is much larger than the offset distance, the inside and outside constraints effectively cancel each other out. So a one-dimensional example showing the heat generated from 4 positions and normal constraints is depicted in the slide. The left image shows the results generated by pseudo-normal constraints with linear and or a quadratic basis function. It doesn't matter. The small dots indicate the placement of the inside and outside pseudo-normal constraints. And the right image shows the results with the MLS method, and the arrows indicate the outward normal directions. So compared to the RBF, which sees the whole data set and can make for very smooth surfaces, the MLS only sees a small part of the data set. It is very local and very cheap to solve, but it can be easily confused by significant noise in the point cloud. Let us switch to considering the Poisson surface reconstruction. Poisson surface reconstruction is a very popular state-of-the-art modern method from 2006 that has been updated continuously over time. It performs global fitting of an indicator function using partial differential equations that is robust to noise, sparse and computationally tractable framework to solving this problem. Informally, given a set of oriented points, which is like the set of points that is equipped with oriented normals, in this case the normals are depicted pointing inward inside the shape. Our goal is to reconstruct an indicator function that is very similar to the occupancy function that we have been studying previously. Because we don't know the indicator function, we will instead solve a different problem. We will estimate the gradient of the indicator function. The gradient of the indicator function should be exactly equal to the oriented points that we have observed previously. But the gradient of the indicator function is a continuous function defined in a three-dimensional space. However, the points are discrete, so our goal will be to fit the gradient to the points. Then, using the fitted gradient, we will reconstruct the indicator function by solving the Poisson equation. The Poisson equation is depicted in this slide. So this amounts to Poisson surface reconstruction. The Poisson surface reconstruction is an advanced method that has been applied to a number of cultural heritage conservation projects. For example, it has been applied to reconstruct Michelangelo's David statue. The original statue had around 1 billion points, in fact, from a number of laser stripe scans. Specifically, it has produced a 22 million triangle reconstruction in under a few hours. This was back in 2006. These days it will be much faster on modern compute hardware, and the detail of the reconstruction you can observe in the next few slides. For example, it is capable of reconstructing actually the chisel marks on the surface of the head, and then also the drill marks in the hair of the David statue. And you can also observe how detailed is actually the reconstruction of local regions such as the eyes, for example. Most often we will use the Poisson surface reconstruction framework when we are referring to non-learned reconstruction methods in practice. Let us switch to studying neural approximators for implicit functions. So when we switch to learnable methods for reconstruction, for example, our goal is always defining the appropriate representation for the reconstruction. So let us talk about the representation that can be used for 3D reconstruction. So as you know, and we have extensively studied, that several 3D output representations are available, and all of them have been proposed over the course of the years for learning-based 3D reconstructions. So as you know, voxels are a straightforward generalization of pixels to the 3D domain. They partition the 3D space into 3D cells or voxels according to an equidistant grid, and the size of each voxel determines the granularity of the representation. And this comes with a severe limitation, in particular context of deep learning. The memory requirements for 2D images grow quadratically, and for voxels they grow cubically with resolution, and consequently, if one would convert a state-of-the-art fully convolutional architecture for 2D images operating at a resolution of 512, for example, into a 3D architecture operating on voxels, the network would require a lot of GPUs to satisfy the memory requirements of the resulting network. So in practice, most voxel-based architectures are therefore restricted to very low resolution, or they have to use special tricks such as sparse representations or octrees, as we have discussed previously. Another representation, as you know, of course, are point clouds, and these are very flexible and computationally efficient, especially compared to voxels, but they lack connectivity information about the output. So most existing architectures are limited in the number of points that can be reconstructed. Also, typically a few thousands are used, so such as the point net architecture, for example. Other works, for example, in this case, AtlasNet work has been mentioned. They have considered meshes comprising vertices and faces as output representation, but this representation either requires a template mesh from the target domain, such as, for example, a head of a person over a hand of a person, or it also sacrifices certain important properties of the 3D output, such as connectivity. So if a template mesh is used, the resulting model is restricted to a very specific domain, such as faces or human bodies. So it is very difficult to construct models that can handle multiple object categories, such as chairs or cars at the same time. Approaches which sacrifice connectivity often result in non-smooth meshes, like the one depicted in this slide. So given the limitations of existing 3D output representations, it would be natural to ask ourselves, can we find a 3D representation for deep neural networks that can represent meshes of arbitrary topology and arbitrary resolution, not restricted to like a Manhattan world, like the voxel-based representations are, not limited by excessive memory and compute requirements, preserves connectivity, not restricted to specific domain, and so on. And so recently there has been a number of works out that this is very recent, from 2019, for example, that leverage the implicit function-based representation for deep learning. So we will cover two of the works. So one of the work is the deep SDF, which represents as shapes a surface by a continuous volumetric field, and the magnitude of a point in the field represents the distance to the surface boundary, and the sign indicates whether this is inside minus or outside of the shape. So because the field is continuous, meaning that we don't discretize anything into like a volumetric grid or anything like that, so it similarly implicitly encodes a shape's boundary as the zero-level set of the learned function, while explicitly representing the classification of spaces being part of the shape's interior or not at arbitrary resolution, because the field is continuous, right? So it also uses a conventional definition of the SDF, which maps 3D points to a real line. And what it proposes is to represent the SDF using a neural network, for example, multi-layer perceptron. So in theory, as a universal approximator, deep feed-forward networks can learn continuous SDFs with arbitrary precision, but of course in practice the precision of the approximation is limited by the finite number of point samples on the surface and the finite capacity of the network. One direct application for feeding SDFs would be construct a training data set of pairs of X and S, where SDF of X has the value S at the point X in 3D, and then we select a neural network approximator and we train it by minimizing a fitting loss that measures how accurately the neural network's value predicts the value of the SDF in that particular point in space. Typically this is done within a clumping threshold, which controls how far from the surface we expect to maintain a metric SDF. And so once trained, the surface is implicitly represented as the zero isosurface of f theta of x, which can be visualized through raycasting or Martian cubes. And one limitation of the described model is that it doesn't model many shapes, it only models a single shape so far. But training a specific neural network for each shape is not feasible or not useful. What we would like to do instead is we want a model that can represent a wide variety of shapes, discover their common properties, and possibly also somehow embed them into a lower dimensional latent space. And to this end, what we can do is we can introduce a latent vector z, which can be thought of as encoding the desired shape, so like a latent code for the desired shape, and it serves as a second input to the neural network, as depicted in this coded shape deep SDF architecture. So now we want to approximate the SDF of the shape indexed by the index I by a neural network which takes an input latent code zi and a 3D query point location x, which outputs which approximates the signed distance function. So during training we have to find both the shape codes and the network parameters by minimizing this kind of a loss, which actually implicitly says that, well, the zi's are coming from a multivariate Gaussian prior distribution with a spherical covariance matrix. So there is a bit of probabilistic machinery involved, but in the end what we solve for is we minimize this kind of a loss function and obtain parameters of the network and is in the actual latent codes for the shapes. So we end up having actually a rich latent space of latent codes, which we can decode and obtain different visualizations by interpolating between the shapes and the latent space. And this is again done by basically raycasting or extracting the mesh using Martian cubes algorithm by evaluating the deep SDF trained network over a volumetric grid of x values. Well, another very similar idea that has been released at the same time is the occupancy network, which actually does the same, but not for a signed distance function, but rather for an occupancy function. So occupancy function is 1 inside the shape and 0 outside the shape. So it's basically the indicator of the shape that we would like to fit. And they do exactly this, well, very similar machinery, and they extract the shape as a decision boundary of a nonlinear classifier that they use the neural network for. And so this yields a continuous implicit surface representation that can be queried at any point in 3D space, and from which watertight meshes can be extracted using, for example, Martian cubes. The simple idea, and there have been a number of such simple ideas recently, it basically solves some of the problems mentioned previously. So, for example, the implicit representation can represent meshes of arbitrary topology and geometry, and it's not severely restricted by memory requirements. It also preserves connectivity information and naturally blends with deep learning techniques. Additionally, as many of the concurrent works show, this model can be conditioned on an observation, such as an image, for example. So in this slide, we can see how multiple different networks, different models can be conditioned on the very same image of an airplane or a chair or a car to represent vastly different shape models, such as the voxels, point sets, or triangular meshes obtained using a variety of representations. So this concludes this video. Thank you for watching.